Up to now we were looking at examples of second order boundary value problems. So today we look at fourth order problem. So the biharmonic operator. So the biharmonic operator is delta square, and therefore it's a fourth order operator because delta, you apply delta of delta. Delta is a second order operator. You apply it once again, and therefore you have a fourth order operator. So we are going to look for Dirichlet problem. So you have Laplacian square u equals f in omega, and u equals du by d nu equal to 0 on gamma. So here du by d nu comes in the Dirichlet problem itself, because for the fourth order operator you need two boundary conditions. So you might have had this experience in the differential equations also when you're dealing with boundary 2-point boundary value problems. So for second order operator you needed one boundary condition. For the fourth order operator you will need two boundary conditions to fix a solution uniquely. So this is called the Dirichlet problem for the biharmonic operator. So if phi belongs to d omega, then you have integral f phi on omega equals integral Laplacian square u phi dx. So now you can transfer the derivatives slowly, and so by repeated application of Green's theorem, because of the fact that u and du by d nu are, and anyway phi is in d omega, so there is no problem, there are no boundary derivatives or of phi or anything, so you get Laplacian u times Laplacian phi dx. Okay, so this is the thing. And now if you look at u in h20 of omega, so this implies what? That u equals du by d nu equal to 0 on gamma, and therefore the boundary conditions are automatically satisfied. And you also know that d omega is dense in h20 of omega. Now both sides of this equation here are continuous with respect to the h2 omega norm, and therefore we have the weak formulation. Find u in h20 of omega such that integral on omega delta u delta v dx equals integral on omega fv dx for every v in h20 of omega. So we have here the space is h20 of omega, which automatically ensures that the boundary conditions are satisfied, and then the linear form is integral omega fv dx, which is continuous with respect to the L2 norm and therefore in the h2 norm and so on and so forth. And now, and the bilinear form is integral delta u delta v. So this is of course obviously continuous. So AUV equals integral omega delta u delta v dx, and therefore you have that mod of AUV is less than or equal to mod delta u 0 omega mod delta v 0 omega, and that is of course less than or equal to c times norm u 2 omega norm v 2 omega. Okay, so this, now you have that AVV is equal to integral mod delta v square, or which is equal to integral on omega delta v delta v. Okay, so now we have seen, I have given this probably as an assignment. Okay, so if you have u and v in d omega, and you look at integral delta u delta v dx or omega, so then you can, so this is what this is. Now slowly you can transfer any derivative anywhere to either side, because everything is in d omega, there will be no boundary terms, and this will then turn out to be equal to sigma over ij equals 1 to n d2u by dxi dxj d2v by dxi dxj. So just transfer the derivatives one by one to from here to here, and then you can prove this. So this is just a you try it for instance with n equals 2, and then you can generalize it for any n. And therefore you have that this is equal to mod u square to, so delta AUU is therefore equal to mod u square to omega, and you know we have omega is a bounded open set, so omega in Rn bounded open set, and gamma equals d omega, and therefore you have Poincaré's inequality, which tells you that this is less than or equal to mod u square is greater or equal to c times mod norm u square to omega. In fact, mod u square to omega itself is a norm, and therefore you have the ellipticity. Therefore by Lax-Milgram, there exists a unique weak solution for f in L2 of omega, and A is symmetric implies u is minimizer for j where jv equals 1/2 of integral omega mod delta v square dx minus integral fv on omega dx. Okay, so over h20 of omega. Okay, and further you also have continuity, because you have that alpha times norm u square to omega is less than or equal to integral mod delta u square dx over omega, which is equal to integral omega fu, which is less than or equal to mod f 0 omega mod u 0 omega, which is less than or equal to mod f 0 omega norm u 2 omega. So by the standard you have norm u 2 omega is less than or equal to 1 by alpha times mod f 0 omega. So you have continuous dependence on the data. Okay, so this is the thing, and as usual you can now convince yourself that if you have a weak solution implies delta square u equals f in d prime of omega, and of course by construction, namely you have the u belongs to h20 of omega, and therefore you have u equals du by d nu equal to 0. Okay, so then if you look at regularity theorems, then we can say that whether it's a classical solution or not, and of course a classical solution is the thing. So now if you have the Laplace equation minus Laplacian u equals f, which minimizes with the associated strain energy, as it's called, 1/2 integral mod grad u square minus integral over omega f grad v square fv dx. So this, you think of omega as a membrane which is stretched over the thing, and it is fixed to the boundary gamma, and it is acted upon by a vertical force whose density is given by f, and then the Laplacian, so u gives you the vertical displacement of the membrane. I am talking of R2. Okay. Now similarly, if you have Laplacian square u equals f, so u equals 0 on d omega. So this is nothing but the bending of a clamped plate. So you assume that you have a very thin plate, which of course is a three-dimensional body, so approximated by means of its middle surface, so that will be a two-dimensional body, and then you have a force which is acted on this, and then clamping the plate along the boundary means that you cannot even, not only that it does not move, but it does not have any lateral rotational movements, etc., and therefore that is called clamping. So when you clamp a plate and then you act it upon by vertical force, then you have the bending vertical displacement is given by this equation. Okay, so that's it. So now we have of course given you a weak formulation which is in H20 of omega. Now generally, from a numerical analysis point of view, if you want to approximate solutions, especially using methods like the finite element method, etc., then H2 is a difficult space because the finite element approximations are very cumbersome and very complicated, whereas it is much better if you work with H1. So we try to give you a mixed formulation, a different formulation which does not depend on the Lax-Milgram lemma, and therefore but it is of a different kind. Okay, so you increase the number of unknowns and then you see. So let us give you an example of a mixed formulation. So u delta square u equal to, so omega in Rn bounded open set and gamma equals d omega. This is delta square u equals f in omega, u equals du by d nu equal to 0 on gamma, and then you have the weak formulation u in H20 of omega such that integral on omega delta u delta v dx is equal to integral omega fv dx. So where f is in L2 of omega. Okay, so now we so regularity theorem. Assume that the weak solution satisfies u belongs to H3 of omega intersection H20 of omega. So there is a theorem of Kondratiev which says that this is true if f belongs to L2 of omega and omega is of class is a polygonal domain, and obviously for much more also. If it's a smoother domain, it will this is about the minimal hypothesis for this. Okay, so there's a theorem of Kondratiev which says that this, so this is not an unreasonable hypothesis. Okay, so now I am going to say sigma is H1 of omega and v equals H10 of omega, and we have A from sigma cross sigma to R. So A of sigma tau equals integral sigma tau dx, just the L2 inner product for all sigma tau in sigma. Okay, and then B is from sigma cross V into R, and B sigma V or B tau V, sorry, equals minus integral on omega grad tau dot grad V dx. Okay, so tau in sigma and V in V. Okay, so and then you have of course that f is in L2 of omega. So theorem, assume weak solution satisfies the regularity condition namely u is in H3 of omega intersection H20 of omega. Okay. Then sigma u equals minus Laplacian u. So u is in H3, so Laplacian u will be in H1. U is in H20, so it's in H10. So this belongs to sigma cross v. Is solution of A sigma tau plus B tau u equal to 0 for every tau in sigma, and minus B sigma v equals integral omega fv for every b in v. So you see, we now have a system of equations with two unknowns. So sigma is an unknown and v is an unknown. So we have increased the number of unknowns, increased the size of the equation, but on the other hand we are working with simpler spaces, namely h1 of omega and h10 of omega, which for approximation purposes is the same. Also, this very often it is not that u which is interesting. If you are, for instance, interested in fluid mechanic problems where the Biharmonic operator occurs naturally in what is called the stream function vorticity formulation, then we are interested in Laplacian u directly. So instead of solving for u in h20 of omega and then differentiating it twice, so you directly try to get an approximation of the Laplacian. So that is why these mixed formulations where you introduce a new unknown is sometimes useful. Okay, so further, solution of star whenever it exists is unique. Okay, proof. So we have sigma equals minus Laplacian of u, and therefore for every tau in h1 of omega, which automatically in L2 of omega, you have sigma tau plus integral Laplacian u tau equal to 0. Okay, and therefore, so this implies that integral on omega sigma tau dx plus, or rather I am going to apply Green's theorem, minus integral over u, you have that grad u grad tau dx, then plus integral du by d nu tau d sigma over gamma, but this term goes to 0 because du by d nu is equal to 0, and therefore you have this is equal to 0. Okay, that is a sigma tau plus b tau u equal to 0 for every tau in h1 of omega, which is equal to sigma. So u is in h3 implies, of course, sigma equals minus Laplacian u belongs to h1, which is capital sigma. Okay, so that is all. Now you take v in d omega. So you have minus integral sigma omega sigma delta v equals integral fv, because you know that delta u delta v equals fv, that is sigma equals minus delta u, and therefore you have this from the weak formulation. So this is the weak formulation. And now once again you approximate by means, once again you apply Green's theorem, you get integral grad sigma times grad v over omega, there will be no boundary term, equals fv. And this is true for all v in d omega. Now both sides of this equation are continuous in the H1 zero norm, and therefore this implies for all v in, so by density and continuity, for all v in H1 zero of omega equals to b. So you have that minus of b sigma v equals integral omega fv for every b in H1 zero of omega. So you have that this pair satisfies this system. Okay, so now we want to show that the solution whenever it exists is unique. So if sigma 1 u1, sigma 2 u2, two solutions of star, then what does this mean? This means that if sigma equals sigma 1 minus sigma 2, u equals u1 minus u2, okay, then you have a sigma tau plus b tau u equal to 0 for all tau in sigma, and then b sigma v equal to 0 for every v in v. Okay, so because you just subtracted the two equations, the fv got cancelled, and this is, so if you now, so if you put tau equal to sigma in the first equation, you get a sigma sigma plus b sigma u, that is 0, but then this is already 0 by the second equation, and this implies that integral mod sigma square equal to 0 on omega, that implies that sigma equal to 0, that is sigma 1 equals sigma 2. Now sigma equal to 0, so this now implies that b tau u equal to 0 for all tau in sigma, and then you take tau equals u, because u is in H1 0, so it's in H1, belongs to H1 0 of omega, which is of course contained in H1 of omega equal to sigma. So if you do that, then you get integral mod grad u square equal to 0, and that implies that u equal to 0 since u equals h in H1 0 of omega, and you have Poincaré's inequality, and therefore you have that u1 equals u2 also. So this proves the uniqueness of the theorem. Okay, so this completely proves the theorem. So now let us look at this equation again. So suppose I have sigma u solution of star, and see how we can recover the equation. So sigma tau minus integral grad tau grad u equal to 0 for all tau in H1 of omega, and you have grad sigma grad v equals integral fv. Okay, for every v in H1 0 of omega. So if you use v in d omega, then this implies that minus Laplacian of sigma equals f in d prime. And the first equation, if you use tau in d omega, then you get that sigma equals integral sigma tau equals minus Laplacian u times in d prime of omega, and therefore from these two together you get delta square u equal to f in d omega, d prime omega. So in the sense of distributions it satisfies the thing, and you also have u is in H1 0 of omega, so implies gamma naught u equal to 0, that is u equal to 0 on gamma. So we now only have to recover the other boundary condition. So you have that minus of sigma tau on omega dx is nothing but integral on omega tau delta u. Sorry, sigma is solution, this is grad tau grad u, and that's equal to integral on omega minus tau times delta u plus tau times du by d nu on gamma. So let us assume that u is in h2 of omega, which is reasonable to assume because sigma Laplacian u is in L2, so you assume that u is in h2 of omega. And therefore, now if you take tau in d of omega, you get that integral sigma tau equals integral over tau of minus Laplacian u for all tau, and therefore in d omega, and therefore this is now completely a L2 situation, and therefore this implies that sigma equals minus Laplacian u in L2 of omega. And then going back to this equation here, this will imply that integral tau du by d nu equal to 0 for all tau in h1 of omega, and then we know, we have already seen this in the Neumann problem. This implies that du by d nu equal to 0, and therefore you have u satisfies both the boundary conditions and is in satisfies the differential equation in the distribution sense. So we can recover the original problem from this weak formulation. So this is called a mixed formulation because you have two kinds of unknowns, which are not only the primary unknown u, but you have introduced another unknown sigma, which is this thing. And so for a fourth order problem, generally we work with h2, but now in a mixed formulation you only work with h1 cross h1 0, which is a big improvement from the numerical analysis point of view, as I already said. Okay, so next time we will see a system of equations which occurs in elasticity.